there's no room for error. It's like it's a bit of a perfectionist. It's the most perfect science you could get, and even mathematics is not perfect, right? If you're choosing your axioms based on intuition, that's a very big problem. You choose your axioms after trial and error.
So today I welcome my guest, Aziz. He's a friend of mine. I met him in a meetup called Curious Minds. So he's kind of an expert in mathematics, I would say.
No, not at all. Well, let's continue.
Relatively an expert from my perspective, because I'm very ignorant about it. So I want to learn more about this topic in general. And we're going to delve straight into it and talk about just in general what mathematics is, how can we actually come to prove mathematical conjectures and all these other things. So my first question to you, Aziz, is going to be how would you define mathematics just in general for a layperson, let's say? Would you say it's just a set of axioms with different, let's say, inferences out of those axioms? So you have, first of all, axioms, and then you infer stuff about those axioms, and then there you go, you have a mathematical.
Actually, let's take a step back. So, it's defining mathematics is not something, let's say, just about proofs and whatnot, right? So, essentially, mathematics is the study of patterns, what things actually are, on the bare minimum, as much as possible. It's not necessarily like it's trying to understand how the world works more than anything else. It's trying to put a language to something to understand how to speak to it, right?
Yes.
That's what mathematics is. Proofs is not necessarily proofs is just to establish this is the right way, or based on certain axioms. But to me, at least, and I think if you talk to different mathematicians, they would I'm not a mathematician myself. I guess I did study it.
Yes.
If you talk to actual mathematicians, they would tell you a different perspective. To me, when I was doing mathematics in college, it was how do you understand something, right? So, for example, you have different branches. Each branch studies something, and then it's applied. That's why mathematics gets applied in economics, chemistry, physics, biology, right? So, try to understand how things work and put it into a language to understand it, if that makes sense.
Yes.
Essentially, it's putting a language, right? That's the key thing. But before that, it's developing to it's trying to create tools, methods, whatever, to be able to read.
Makes sense.
If that makes sense.
Yeah, it does.
In a sense, I'm more of a believer that mathematics is discovered. It's not invented per se.
That was actually my next question. So
because you cannot invent what's already there. You discover it, right? You could modify it, but you discover it, right? So, for example, I remember in in my number theory class. Everybody says the Pythagorean theorem. However, there is some evidence that the Babylonians actually knew about it. I think centuries ahead.
Okay.
There is some evidence, but it's not concrete to say this, or hard evidence to say that the Babylonians knew it. But there is some evidence.
Yes.
So essentially, it's discovered. It's something you observe a pattern, you start to discover a pattern. Then once you discover a pattern, you start to put it in writing to understand how it works, right? But you don't invent it. So, for example, when say people Newton invented calculus, no, Newton observed observed the whole thing. He observed something and was able to capture it in writing, right? So it's essentially like the same with music. You don't really invent new sounds. You discover the sound.
Yes.
You discover the sound.
So you just put different sounds together, and then there you go. You have music, but the sounds are already there in some sense.
In a sense, but even let's say you build a tool to capture the sound, right?
Yes.
If that makes sense.
Yeah.
And that's also I'm gonna jump a bit. One of the reasons you cannot write notes for vocals per se. Let me rephrase. I think that's a different discussion, but you cannot write notes for the human voice, like to capture every single degree. You could write it for a machine. We're able to write notes for machines. That's why you have different musical notes for piano, oud, qanun, whatever.
Yes.
However, the human voice has is a more of a delicate range. It could go like, I think you could go very, very, like it's different. You know what I mean? So it has different octaves. However, a music machine has intervals. It jumps from an interval to an interval, and I think the reason I'm talking about this is not to stray too off for the topic, is to understand what we are. We're discovering things. We're not necessarily, in terms of mathematics at least, we discover how because for example the Pythagoreans did some tuning using number theory for whatever. So you discover, and then what you discover, you see what could work for it, right?
Yes.
At times, that's not for everything, right? So for example, you take some of that math, you apply it elsewhere, right? You could have one mathematical theorem that's applied in multiple cases. Take an integral, for example. An integral is essentially calculating an area of something.
Okay.
So for example, you could use it to calculate space, volume. You could also use it to calculate the amount of interest on loans or whatever. So if you know how something works, you could use mathematics for it, right?
Yeah.
If you don't know, you'll never be able to do it, right?
Yes.
And people make a mistake. Something I hear all the time, that mathematics is, and specifically here in Saudi, mathematics is a bit useless. That's how people view it, honestly.
Especially in school, like primary school and stuff.
Well, that's a different problem, because honestly, there are two parts. There's the part that we have actually pretty good curriculum for mathematics in Saudi. However, the way we teach it is absolutely boring.
Yes.
I remember in my senior year of high school, we were doing calculus for the first time. I'm like, how the heck does that work? I'm like, okay, if you take the derivative of this, you get the maximum. Why does it work? That's my own nature. Like, I'm curious about this. Why does it work? It's interesting. And I remember even when I was doing a logic class back in university, my professor did his undergrad in mathematics, then went to philosophy. He said something, hey, learning calculus, the way that we teach mathematics is like, how can I use it for engineering? How can I use it for business and whatnot? I don't think there is something inherently wrong with that, but however, it's a limiting perspective. Yes. A bit.
Exactly.
So my professor was saying just learn for the sake of learning it, right? So for example, most people do calculus and whatnot, but for example, we start with number theory, abstract algebra, and do the genuine nice proofs on how the machine actually works, it's way more interesting just computing, because it becomes a puzzle. Doing proofs is more of a puzzle than computation. Computation is like essentially, it's a puzzle as well, but it's not as puzzling as a proof, if that makes sense. Yes. When you do an integral, for example, integrals are why people struggle with integrals compared to derivatives. Derivatives is easy, it's just computing. Integrals has this puzzle component. What do I need to do to complete the computation? So it's like it becomes puzzling. It's a puzzle. People start hitting a snag where it becomes a puzzle. But for example, if you learn, let's say, number theory is easily understandable in terms of a problem, very difficult to do in terms of a solution. It's much more difficult. Contrary to analysis, where you spend most of your time understanding the problem and less time on the solution. Abstract algebra and number theory are the other way around. You understand the problem, but you spend your time doing the solution way more.
But I guess it depends also on the context. Like, if you are going to, let's say, if you're going to produce a solution, then you need to understand the problem in any context.
Yes.
In some sense. So I guess it depends on the context. If the solution is out there, or it's relatively not there yet. So for example, for Mazda's theorem, so before it was solved, you need to understand the problem, and you don't have solutions, let's say.
Yeah. For Mazda's theorem, it's a very easily understood problem. I understood it since I was like my very first class of mathematics in college. I understood what it meant. It was very easy to understand.
But then
the solution, I think, anybody who you tell them what's for Mazda's theorem with a very basic grasp of mathematics, they will understand what it means.
Yes.
But no one is gonna solve it.
Exactly.
Like, not no one. Andrew Will solved it, but most people are not gonna be able to know how to attack it.
Exactly. Yeah.
But for example, analysis, I could give you a problem. Like I was doing in grad school, I would read a problem, And I'm like, okay, what does this mean? Before I even could think of a solution, I need to understand what it means. That's what I mean. There are two types of problems. There are problems you don't understand what's the problem, and then there's a type of problem you don't know where to begin. There's that. Those are two different things.
Yes,
those are two different things. In analysis, in mathematical analysis, you have a harder time understanding what the problem means. Then once you understand the problem, it becomes relatively easier. But when it comes to algebra and number theory, no, you can understand the problem easily, most of the time at least. But you struggle big time to know where to go and whatnot.
Yes.
But I think if going back to school, it's because the way we see it, right? And even when I was teaching back at Central Michigan University, I was like, people treat mathematics as this big boogie monster. In a sense, and I think because there's no room for error. It's a bit of a perfectionist. It's the most perfect science you could get, and even mathematics is not perfect, right? Because there's a very fatal flaw in the whole how mathematics works.
I think Godel's. We'll delve probably into it in some sense.
Sure, let's
from a philosophical aspect, not from mathematics.
Yeah. So Godel's theorem. I think there are two. By the way, there's the misconception. There are two problems. One. So before we go into it, let's explain how mathematics really work, right? So mathematics works actually by establishing definitions and setting axioms, okay? Because you cannot prove everything. So axioms are things we take for granted as true, regardless if they are true or not, but we assume they are true in a sense. Yes. Definitions are, in a sense, are axioms, but to define something to limit it. Because if you don't limit it, you keep it open, it just gets lost. So the way mathematics works, use definitions and axioms. So in Godel, so essentially those are the sets of rules you play with, right? So you try to do problems based on these sets of rules.
Yes.
Okay. So a good example of this, one of the millennial problems, which is the Riemann hypothesis. The Riemann hypothesis is still unsolved. However, if you assume it's true, you just assume it's true, you treat it as an axiom, you could get lots of results. Right? However, if that problem is you remove, and one day that problem becomes false, or that somebody proves that the Riemann hypothesis is not true, all of the results that we generated from it falls apart. It completely goes away because now you were relying on an axiom that sets you up for big results. So once you remove it, you remove it.
Okay, gotcha.
Okay, so now going back, you're talking about completeness theorem. So there are two. One, there's no axiomatic system that proves its consistency. You know what? So you need a bigger system to prove that system, and a bigger system to prove the bigger system, and it just keeps going and going and going. So essentially, you can never prove the system you're using is consistent. So you have to take it essentially on face value. Then the other problem is proving there are statements that we don't know if they are true or not. You cannot prove within that system.
Yes.
However, if in a bigger system, it can be proven. It can be proved if there's a system, but do we know if such a system exists? We don't know.
But consistency in this context means that you can actually prove every statement within that language to be true. So if it's consistent, you can prove all statement in that language based on the axioms to be true. If it's inconsistent, then you can't prove all statements.
No, that's not the case. The case is based on, if I give you 5 axioms, there are multiple statements that come out of that axiom, many. You cannot prove all of them.
Makes sense.
So you need a bigger system to be able to prove the statements that came from that system, and so on and so forth.
Yes.
But going back, what I meant is, if I give you 10 axioms, you cannot prove its consistency. You need a bigger axiom system to prove its consistency.
Okay, makes sense.
Consistency means there are no contradictions. Do you know what I mean?
Okay. Yeah.
That's what it means. So I could give you 5, 6, 7, 8, 10 statements. If you compare them to each other, they're not necessarily
contradicting each other.
Okay.
So there is no aspect of truth in an absolute sense. It's just the contradiction part.
It's a relative truth to the axioms. It's a relative truth to the axioms. Again, axioms we take as truth.
Yes, that's why he said it's not perfect. He even mathematics is not perfect.
Yeah, mathematics is not perfect.
Because we can't absolutely prove the axioms are true in some sense.
Yeah, in some sense. So you take it as faith value. And when I say faith value, but here's the thing, when it comes to mathematics, they're very careful when it comes to picking their axioms and definitions. They are taught to be very precise. So that's why I say this is the closest to perfection you're going to get in terms of systems, right?
Yes.
That's so the bigger the problem is, the more axiom, the more variables you have, the more axioms you need. I think that's what I would say.
Okay, makes sense. So that's how they get to axioms. Basically, they infer a few axioms and then they deduce certain statements from them, and then they might go back to this axiom system and add to it, basically, as they're going or as they're progressing. So that's what you're saying. Yes. And that makes sense. And I think even to go back to the discovered and invented stuff, is one person actually mentioned that mathematics is discovered, but the notations are invented in some way. So it was like it's almost like a hybrid of invention and discovery.
Yeah.
So that's an interesting aspect of it. And would you say that mathematical ways of understanding are always the optimal way to understand things in general? Because if we put it in the context of physics, for example, you can actually describe the physical world with regards to equations, but when it comes to human consciousness, you can't really describe it with regards to mathematical equations, I guess, or as neat as the physical world, let's say. So would you say that we'll always have a better understanding of things if we have mathematical equations to them, or not necessarily?
This is a very difficult and complicated question, a nuanced question that I'm not going to be able to answer.
But in general,
take what I'm going to say with a grain of salt.
Yes.
Neuroscientists have to understand some computational mathematics. I'm not. So there's people actually use mathematics to understand people's behavior. So you have mathematical biology, you have mathematical psychology. So no, there are. But I'm not exposed a lot to know what's going on about them. But for example, you use mathematics to do game theory. If this happens, that happens. So I think it can be, but I don't know. I'm not gonna say something that I've not read about a lot.
Yes, that's true. I think even there is like aspects of mathematical biology, for example, but when it comes to things that are as complex as human consciousness, for example, you can't really describe it with, let's say, mathematics, at least up to this point. So I think inherently we have a better understanding towards things we can compress in mathematical equations. Because if you look at, for example, human consciousness, as I keep bringing this example up because I think it's the best example of a complex system. So if we contrast it to the physical world, we actually have much more understanding of the physical world than human consciousness, because we can describe it in equations, basically.
You cannot describe something in equations unless you understand it good in a way.
Of course, yes.
So I think if I understand, correct me if I'm wrong, I understood you, I think you have it the other way around. We have notations for the physical world because we understand the physical world. We don't have as much, again, don't quote me on this.
Yes.
Regarding consciousness, do we really understand what's consciousness to begin with? So if you understand consciousness, if you understand something, it's not necessarily you would be able to put it into mathematics. But if you don't understand something, you would definitely not be able to do it to mathematics. So, okay. So now we're coming to necessary and sufficient, right?
Yes.
Understanding something is necessary to be able to put it into mathematical language.
Yes.
However, understanding something is not sufficient to put it into mathematical language. I don't know what would be sufficient to do it. So there are two things.
Gotcha.
So the difference between necessary and sufficient. So necessary means
it's
a must.
It's a complete description.
No. Necessary, something is a must. Sufficient, something is enough. So in a sense, let's make it a simpler problem. If I told you I was home at 8 p.m., okay, it's a necessary condition for me to be asleep at my own bed at home. However, that fact on its own is not enough to conclude that I was sleeping at my home at 8 p.m.
Yes.
So you need other factors to know. Does that make sense? So, however, I'm not like, you cannot say, if you told me where were you at 8 p.m., I said at home. So you cannot just jump into the conclusion that I was sleeping at my room, right?
Yes.
So, for example, if you told me where I am at 8 p.m. and I told you, well, I was at a restaurant, you say, okay, you weren't sleeping in your room then.
Yes.
So essentially, the idea of this is, and if the necessary condition is not there, that means whatever you want to infer from it is not true.
Okay.
If the necessary condition is there, you still cannot infer that's true.
Yes.
The sufficient condition, on the other hand, you could infer that that's true.
Yeah, I got you.
Okay?
Yes.
Yeah, I think that that's the case.
Yes. So would you say that delving into philosophical things about mathematics is actually useful to, let's say, solving problems, or is it like kind of separate? So you have the philosophy of mathematics and then you have mathematics. Would you say that they're in some sense complementary, like understanding the philosophy is important to actually solve the problems, or is it irrelevant and it's just like an additional thing to do?
I think, to me, philosophy is more personal, right?
Mm.
You could understand, like you could start doing problems, you could do proofs, but understanding the philosophy of mathematics is a deeper connection. I think philosophy is a more deeper connection to things. I think philosophy even goes to, that's just my view, it's a deeper level of mathematics. It's like it goes into a deeper level than mathematics actually does.
Yes.
It's actually, in a sense, it's a romantic relationship with something. I think it's, when I say romantic, I think it's like you're trying to understand this thing so well. So you jump into the philosophy of it. That's why you have the philosophy of mathematics, the philosophy of psychology and whatnot. That's a different thing. It's like, it's trying to, it's a deeper connection.
Yes. So it's almost like an additional thing that someone who's too passionate about mathematics would delve into, but it's not a necessary, let's say, condition to actually do mathematics, let's say.
Yeah, it's not necessary, because you can do mathematics without loving the philosophy of mathematics or understanding the philosophy of something.
Yes.
That's how I see it.
Yeah, so would you say that axioms, as we said, like we mentioned axioms previously, so would you say that they are based on human intuition, let's say, in general? Because we see in, like, for example, quantum mechanics, when people get to certain conclusions, they say that we should throw away our intuitions, for example, because quantum mechanics has proved to us that certain things contradict each other or whatever. So would you say that axioms are actually built on human intuition, or is there another thing that's related to axioms?
So axioms are not built on human intuition alone. Axioms, I think they come after a while of observing and whatnot. So essentially, human intuition is, human intuition, I think people mistake the two. Human intuition is not necessarily tell you this is the way. You go for it. Axioms, no, you build axioms, you update them. Axioms are in a sense your principles. So how do you choose your principles? You don't choose your principles based on intuition. You choose them after experimentation. You know what I mean?
Yes.
So axiom becomes an axiom, I believe, after a big or there's some truth to it. You know what I mean?
Yes.
So
in the actual real world. So
yeah.
you actually observe the real world, and then you move on to the whatever axioms you're trying
yeah.
to use.
So for example, if you take two children, one would believe that their mother would love them unconditionally because they observed it. The other does not. Why? You cannot then just conclude. It's relative. I think it's complicated. It's more complicated to say axiom is just intuition. No, axiom you build due to conditioning or observations.
Yes.
Conditioning is something different, and axioms are not always true. I have to say this. Axioms is we think they are true. We take them as face value they are true.
Yes.
So once an axiom falls, everything that has been built upon it falls with it.
Yes.
If that makes sense.
Yeah. But I think even like the observation, like I would kind of disagree with this point, because even observation requires some kind of intuition initially. So if you say like 1 + 1 = 2, for example, that doesn't seem to me like it requires any experimentation. It's something we already have in some sense in our minds as intuition. So I think even to make sense of any experiments, you actually require some kind of, I would say, intuition. But as you said, it's a chicken and egg problem in some sense. Like how can you actually definitively know if experiments are prior to intuitions or intuitions?
So intuition, let's say intuition tells you, let's hold this true. So intuition is telling you where to look. It's not about establishing axioms. Intuition tells you where to find your axioms, where to find truth, essentially. It's not, as you said, it's not, you don't choose your, if you're choosing your axioms based on intuition, that's a very big problem. You choose your axioms after trial and error. Intuition tells you how to start the trial and error process. Those are two different things.
Okay.
Okay.
So there's like almost a feedback between those two in some sense.
So intuition tells you where to go. Then after observations, okay, that's an axiom for me as of now. Until one day, if ever that day comes, something proves it wrong. You know what I mean?
Yes.
So, for example, I don't know. I'm not like, I think that's one of the. So, for example, if that's why we have the black swan problem. I think that I'm trying to come up with my own words for this. So, for example, Sim Nicholas talks about the black swan problem and whatnot. But why did people believe for the longest time there are only white swans? It's because they've never seen a black swan. They've seen millions, maybe billions of white swans. Then they say, okay, all swans are white. So their feed loop gave them an axiom. But was it unrealistic to grab it? Probably. So that's why axioms come based on trial and error and experimentation, right? So you assume if you never have an earthquake for 1 million years in one spot, let's say you were able to have 1 million years, you never had an earthquake, can you assume you're never going to have an earthquake? Most people would have that axiom subconsciously. But once it happens, the whole belief is shattered. The whole belief of safety is shattered. So axioms, in a sense, we build our own axioms. I build my axiom, I'm safe because I have food, shelter, and I'm in a safe country. Once one of those elements change, your belief starts to crash. Your whole world starts to crash.
Yes.
And that's what an axiom is. So axioms, you don't even consciously know they are there. That's why, for example, when it comes to psychology, you find people coming from abusive relationships or whatever. They have this axiom that they're meant to suffer or they deserve this. But once this axiom gets sheds away, their whole world collapses and a new world gets built in. So axioms are the building blocks, even of human behavior, because it's different. We believe in it in a very deeper level than we think.
Yes.
The difference is in mathematics is more objective. It cannot be just subconscious. It has to be conscious. So human consciousness and subconsciousness is riddled with axioms, big axioms. You don't know that you have these axioms. Even if you say they're not true, you deep down you believe these are true. You take them as axioms, and these axioms are not necessarily healthy, nor are actually true.
Yes, yeah, that makes sense. But I think even as well with regards to intuitions, there are certain things that are almost like first principles. So you have like the very basic intuition stuff that can't change. So what you mentioned is things that can be actually disproven by experiments, let's say. But I think there are certain principles such as the law of contradiction. So two things can't contradict each other. So this is a part of intuition that can't, in some sense, be disproven by experiments. So I think there are like two layers of it. Sorry?
What do you mean?
I mean, like, if two things actually seem to contradict each other, we can't infer that those things actually exist at the same time. You get the point? So if I have, let's say, you can't say that a circle square exists because those
What is it?
circle square.
Circle. Okay.
So you can't say that a circle square exists. So that's the law of contradiction because we know that a circle and square are two different things. They can't be the same part. Let's say they can't be the same thing. So
It's not necessarily contradictions. The reason is the circle and square are not the same thing because the way we define them.
exactly, but yeah, I get this point. But we actually predisposed that those things can't contradict each other as a principle, even prior to us defining the circle and square. So we actually, in some sense, had a predisposed principle that a square cannot be a circle and a circle cannot be a square. So they have to be two different things.
We decided to define them like that. Let me tell you, we defined them to be like that.
Yes.
I think what I'm trying to say is a circle and a square are not the same based on their definitions in mathematics or the way humans look at them. Oh, those two look different, they're not the same. But can a circle and a square be actually the same? Well, let me think for 1 second.
Yes.
A circle, for example, I think there's the problem you can squaring the circle. You cannot have a circle and a square with the same size, same area.
Yeah.
Don't quote me on this. I think somebody came close to solving it. I think Ramanuja or something. Let's assume for the sake of the argument, the circle and the square the same. You have to define same in what sense?
Yes.
Right? Are they same in terms of area? If I give you one example, then yes, they can be.
Yeah.
You know what I mean?
Yes.
So they're not necessarily contradictory to each other, right?
Yeah, yeah.
So even contradictions are based on axioms and definitions, right? So an odd number is the opposite of an even number because we define the pairings. Why? Because an even number is divisible by 2, an odd number is not divisible by 2. Period. That's why they're opposite, because you have 1, 2.
Yes.
Okay? So you cannot have an even number that's an odd number and vice versa because the way we defined it. So the contradictions came from definitions. Okay?
Yeah.
But for example, an odd number and an even number, if you take number 7, 6, 5, 4, 3, 2, 1 are all the same to number 7. They're relatively prime to number 7. Okay? So when you talk about primes, for example, so in a sense, the even number and the odd number are the same to that number. So you have to define what are they the same in respect to, right?
Yes.
You have to define which aspect. You're telling me the square and the circle are the same in what sense? You have to tell me why they are contradictory to each other. Are they contradictory? For example, a triangle and a square can have the same size, 100%.
Yes.
But why they are not the same? Are they contradictory? No, they're different. They're not contradictory. Because contradictory means what you just said. Contradictory means if this is not true, then this must be true. Okay?
Yes.
But a triangle is neither a circle or a square. So you cannot tell because the object is not a circle, hence it's a square. If that makes sense.
Yes. Yeah, I get what you're saying, I guess, in some sense. But I think the second point I wanted to ask about you, like moving away from this point, is about proofs, basically. So would you say that, as opposed to science, for example, science is a very social, let's say, kind of action. So people usually socialize when they're doing science, at least from my perspective. And academia and all these things, people usually write papers, they debate and all these things. So would you say the same applies to mathematics, or is it very much of an individualistic, let's say, type of approach, so everyone would solve the whole problem and then publish it, rather than just have it in a gradual way, let's say?
So let me take a step back. When you say social, what do you mean by social?
Meaning that when they're actually solving the problems of this specific endeavor, they're actually consulting their colleagues and then coming back to the problem again. So it's almost like an ongoing process rather than just finishing the thing and then...
No, I think it's the same case for both, right? You could have scientists working on their own, you could have mathematicians working on their own.
Yeah.
So I don't think there's difference. Mathematicians collaborate as well. mathematicians do collaborate, scientists do collaborate.
Yes.
To which field, more or less, I cannot tell. I've not thought about it, but I'll tell you, both spectrums exist.
Yes, yeah, sure. I think it also depends on the personality, I guess, in
But
some sense.
mathematics, I think, is when you're doing a problem, you must understand it more than like. When you come to a mathematical discovery, I think you must understand, like, okay, here's the difference. In science, you could have something that works and you don't understand why. Okay?
Yes.
You have a room of trial and error and whatnot. You could experiment. It works, but you don't know why. In mathematics, because I don't know if there's a field called probabilistic mathematics that I don't know much about. But mathematics, in order to publish, it has to be 100% true.
Yes. You have to know why you came to that conclusion
Yes.
every step.
Yes. So you could come up with something. Okay, this works, but why does it work? At times, you could have a machine that works or a program, but you could have something, and it could go for a while. For example, if you look at. But here's the danger of using something you don't know why it works. It could backfire big time, and that happens in. That's why scientists are like here when it comes to you talk about practicality and perfectionism, right? Practical people would use something. Oh, it works good enough. Let's use it. It works good enough under 1, 2, 3, 4, 5, 6, 7, 10, whatever conditions. But if you change the conditions, it could fall apart.
Yes.
That makes sense. So
Yeah.
it's in a sense, you could have a discovery in science, but if you're not careful where it works, you like because science, let's say physics. I don't know about physics or chemistry. Depends on. Okay. Let's use a very ridiculous example. Let's say these chemicals are always in this state. We could not observe them happening in a different state. But let's say there's a new element that comes in. We don't know about. Let's say, can we say that periodic table is complete? No, we cannot. Like we assume it's complete.
Yeah.
I'm not gonna question that it's not it's complete, but assume a new element appears, then it would change the way we view. Like we could get new conditions. If that makes sense.
Yes. We might go to different planets and discover new elements or something like that.
Yeah.
Yeah.
Yeah. But when it comes to mathematics, it's the conditions we derive our conclusions from are set. So we keep getting more conditions and we put conditions. So once that conclusion is reached, the preconditions are set and it's never going to change.
Yes.
Because the conditions are very well defined in a sense.
Yeah.
In science, in chemistry specifically, more or less, yes, we assume, I think there's an assumption that it's well defined, and it's pretty well defined, but if something new comes, I think it's going to change the game. To what extent, I don't know. It's not going to change how the elements interact with each other, but that new element could help us discover a new property for these elements. I'm not good at chemistry, don't quote me on this, I'm just talking out of my butt at this point.
So my second question, or third or fourth question would be, so how would you basically distinguish between proving a mathematical, let's say conjecture, theorem, whatever, and verifying that something is true in mathematics? Is there a difference? So for example, if you come to me and give me an already set proof, is it easier than me actually going on and proving it? Or is it the same thing to actually verify a proof?
I'll tell you something. That's just my own personal thing. I hated verifying proofs. Because verifying proofs, if it's, okay. Verifying proofs is, to me, it's something I've always hated. Verifying proofs is way more annoying than doing a problem.
Wow. I didn't expect that, to be honest.
Yeah.
I thought you would say like...
No. I might take a longer time doing a problem, but verifying proof, you need at times to... If the proof is not well written, it'll confuse the hell out of you, right? So for example, I remember reading a proof in Rudin's book. Okay, I understand how the proof worked. But I don't know how did he come with that idea. So, in a sense, verifying a proof. Let me rephrase. I don't think it's easier to do a proof than verifying a proof. I think doing a proof is more enjoyable than verifying a proof. In a sense, because it's
so human psychology almost.
Not human psychology, but because let's verifying a proof, you have to dive into the writer's mind. You have to understand why they came up, right? So at times they're gonna come up with this, like, when you see a proof, how the heck did you come up with this idea?
Yes.
It's gonna be alien to you, right?
You have to break the pieces apart and just see how this person came to that conclusion.
Yeah, because there's a big element of playing with different things in a proof, right?
Yes.
A proof is essentially, how do I say this? It's different. There is a trick, it's a puzzle. It's like you're trying to understand how somebody builds something. You're not like they built it, it works. You could have multiple proofs to the same problem, by the way. It's not necessarily one. So one proof would be easier to you than the other one. If that makes sense.
Yes.
So I remember at the same time when my professor did the proof, my professor went through a whole, my professor's proof, I think it was 2-3 pages, and in the book it was half a page. And I remember I hated my professor's proof because it was too long, and I liked the other proof. But then I thought about it. I don't understand how my professor went to every single detail, or do this, do that. It's like it went to the nitty gritty of stuff. That proof is condensed. You don't know how it came. You know what I mean?
Yes.
So there's a long way and the short way of doing something. At times, not all the time.
Yes.
At times there's a long way and short way of doing a proof. The short way at times it requires more knowledge. If that if that makes sense. So verifying a proof is it's like to me it's like grading. I have to be very careful, and it requires more work than doing a proof.
Wow. Yeah.
Doing a proof, when I say more work, it's like you have to think carefully with what the person is saying. You have to read between, you have to be very careful to understand. You have to follow. You're following somebody else's train of thought. That's why verifying a proof is more arduous than, at least in the short term, more arduous than doing a proof.
Yes, yeah, that also makes sense to me with regards to my experience with writing. I think when I just start to write my thoughts straight away, it's much easier for me to write rather than just go back, read, and then come back and write. Because you have other people's perspective, and now things become more complex, if that makes sense. As opposed to you just starting to write your thoughts, random thoughts, it's much more easier, I guess. So maybe it's kind of similar to that situation in some way.
Yeah, no, I don't think I don't think the situations are accurate, because once you do a proof, you have to be very careful of writing it. It's a different problem. You are trying to be clear.
Yes.
You're trying to communicate. When you read a proof, you're trying to understand. It's a two different. It's a difference between listening and speaking.
Yeah.
And I think it comes. I'll retract most of my statements. I think it depends. It can be both ways.
Depends. Yeah, makes sense. So the next question would be about infinity.
Okay.
So infinity as a concept is something that's hard for me to even grasp. I don't think I understand it at all. But how content are you with the idea of infinity? Do you think it's understandable from a human perspective, or is it something too complex for us humans to actually understand to begin with?
Infinity is I remember when I was 5 and people would tell me the numbers keep going on forever. That fact was scary.
It doesn't even make sense, to be honest. Like it does make sense, but at the same time, I don't think it's fully understandable in some deep way.
It is, because you have to understand. I think there are two types of infinities, not just one. I think that's people would need to realize.
Yes.
There's a listable infinity, and at least in numbers, and then there's unlistable infinity. People use the correct technical terms, countable, uncountable, but we technically can never count. It's a listable.
Yes.
If you take the integers, you could list them.
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, da 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 da. You could list them in an order.
Yes.
You can never miss one of them. Okay? You could just list them. If you write a program that will go forever, it's gonna capture every single one. You could plus and minus.
Yes.
Even rational numbers, which is fractions, you could list them. When it comes to real numbers, you cannot, because there's a proof. It's the contours diagonal. You cannot list all of the real numbers. You cannot write them all down, because no matter what you do, you're always gonna miss one. You're always gonna miss. You're always gonna miss, because we don't have a mechanism. There's no mechanism to count it or list it. Sorry, there's no mechanism. No matter what you do, because listing is based on an idea.
Yes.
You cannot list it. You cannot list it at all. But at least in the real numbers, you could order that. Like you could say this is bigger than that. Then you go to the complex numbers when you cannot even know what's bigger and what's smaller, right?
Wow.
Because there's no definition what is bigger, what's smaller. So, in a sense, infinity is scary because it's the unknown.
Yes.
Having something finite, it's known. Infinity is unknown.
Yes, we've never experienced it in the real world, I guess, in some deep way.
Yeah, imagine if you go to the desert and there's nothing around you, just space. It's kind of scary.
Yeah.
Like if you just look no mountains, nothing, just endless space.
Yes, yeah.
You're not confined, no matter where you walk. It's a sense of being lost. No matter where you go, it's never gonna end.
Yeah.
And essentially, I think that's, to me at least when it comes to life, I think what makes life a bit interesting, because it has an end. It's not an infinite life.
Yes.
It's actually infinitely finite, because concept of time depends on real numbers, and that keeps going down. But anyhow, yeah, I think the concept of infinity is scary because it becomes unknown.
Yeah.
And the unknown is scary. The unknown is scary because it takes more effort than the known.
Yes. And would you say there is examples of infinity in the real world that doesn't exist?
I don't know. No idea. Honestly, I don't know. I'm not big into space or whatnot, so I don't know. I don't know if there's an example or not.
Yeah, I think it's conceptually, for me, too difficult to actually grasp space as an infinite thing, to be honest. Like, I think it's almost not possible, but there are certain people who claim it is. We should understand their claims, I guess, but for me, it's something that it's almost not possible, to be honest, for a space to have an infinite regress of things, let's say. It doesn't make sense to me as an idea, but...
The infinite?
Infinite regress, like space being infinite and all these things.
It's okay. It doesn't make sense. Like, yeah. So it doesn't make sense in what sense? Like, I don't think it matters to you. I don't think it matters to me. I think it matters to... I'm more of a believer is, yes, the concept of infinity is there. I think you should take the muse of it and accept that you don't know. And accept you're not gonna know some things. You don't need to know everything.
Of course, yes.
And I think that's just me. I think I tend to avoid if I feel I don't, and that's not a good thing in every sense. But I feel from my own personal perspective is like I don't. I shy away from the things that I feel I'm not gonna understand at times, which is not a good thing. I get scared of it. But once you accept it, either you have two solutions: either learn it, or accept it's not for you and accept it as it is. You don't need to get scared or bewildered by it.
Yes.
There's always going to be something you're not gonna. But even if you look at knowledge is infinite. Like there's so much. I have the axiom that knowledge is infinite. You cannot learn everything. You don't look at martial arts, for example. You have multiple types. You think you've figured it out. Where wrestling, jiu-jitsu, boxing, kickboxing, Muay Thai, taekwondo, whatever, all kinds of movements, all kinds of things. Have we covered all of the movements possible? I don't know.
Yes.
So it essentially, I think there's something we call infinitely finite. Infinitely finite numbers are essentially like largely infinite. Sorry. So
you can always add one more thing, basically.
One more thing. So if I told you, you have five, you have to do 10 moves. You have 10 moves to do. You have 5 choices of moves. So that means the first move you have 1 of 5 choices. The second move you have 5 choices. So that's 5 to the 10th. 5 to the 10th is a very large number. It's a very large number, if that makes sense. Yeah. I don't know why I said 5. Let's say 10 to the 10th. You have 10 moves, 10 slots. You're talking about million times a million times a million times 10. What's that number even called? You know, it's just the amount of things you could do easily compounds.
Yes.
Easily compounds.
So you're almost saying that infinity is even condensing itself into knowledge as well.
Yeah.
So, yeah, in some sense. And I think even Karl Popper, a philosopher, once said that you can always know what you can always verify what you don't know, but you can't verify what you know, if that makes sense.
Yeah.
Yes, exactly. And I think we can disprove things, but we can't completely prove things, if that makes sense.
Yeah, so essentially most of our proofs go by contradiction.
Yes,
So we can
disprove, yeah, exactly. We can disprove things in the world, but we can't confidently prove things, if that makes sense.
No, I think you could prove, let's go back to the contradiction thing. So I think you can only prove using different, I think there are multiple, if I recall correctly, you have proof by induction, proof by definition, proof by contradiction. Proof by definition is based on what you define. Proof by induction, I think it's similar to proving by definition. Proving by contradiction is essentially you assume the opposite and you go through and you discover it's false, then you assume the truth. It's there. You cannot assume something to be true and prove it. You have to prove the opposite is not true.
Yeah.
But you have to define what is the opposite.
Exactly.
Not all things are opposite of each other, right? You have to define what's exactly the opposite. If you know what something is not, you have a more realistic chance of proving the validity of it.
Exactly.
You know?
Yeah, makes sense. So moving away from, I guess, the abstract stuff, let's move on, I guess, to the more practical things. So you, in some sense, had an experience with teaching.
Mm-hmm.
So there is one quote I wrote here is, in learning you will teach, and in teaching you will learn. So has your experience with with teaching, how was your experience with, for example, teaching? Did you learn more stuff teaching than reading, for example, or is it similar? How would you contrast, for example, reading and writing to teaching, actually engaging with people? Would you say it's more superior to other forms of?
They're complementary. You cannot teach something you haven't learned.
Yeah, obviously, yeah.
However, once you teach, you realize you don't understand something as well as you have.
Exactly.
You get asked the weirdest questions. I remember, I taught mathematics in the mathematics center for 4 years. In the first 2 years, I hated doing the basic stuff. I hated them. I was like, let me grab the cool problems, calculus and series, whatever. Like I like taking on the difficult problems. In my third year, you know what? I'm tired. Like something, I don't know what happened exactly, but then it's like when I was explaining abstract algebra, like a very basic problem in high school algebra to a student. Oh, it's fun actually, because you have to think about it. You have to think how to explain it.
Exactly.
And you learn, like you start to see the simple problem and a more complex problem, like how to break it down further, how to see it clearly. So teaching forces you to break down things more, and while you break down things more, you could learn more. If that makes sense.
Yeah.
I have not done research in my life. Honestly, it's my biggest regret. Not a regret. Hopefully, I'll make it up. I've not done research. I think, and that's just based on somebody who has not done research. I'm gonna throw the conjecture out there. Teaching helps you become a better researcher because it forces you to think more. It forces you to write better. If you treat teaching as a chore, then it's gonna become boring. But if you teach it as how can I break down something and you're enamored by it, it's something different.
Yes.
It forces you to learn more. It forces you to connect with the thing you're trying to teach.
Yes.
It forces you to understand it more than just learning. Learning it, you learn for a perspective. You learn for a tool, a means to an end. Teaching is to understand. It's different. It's more complex. It's intricate.
Yes.
And I'll tell you something. I would rather take doing something for 8 hours is way more difficult than teaching that something for 4 hours. Sorry, teaching that something for 4 hours or less time is way more complicated than doing that something for an extra amount of time. So, teaching is more difficult. Teaching shows you something else. Even if you think you understand something, Einstein had a quote. If you understand something, you can explain it easily enough. If you don't understand, you don't know, and I think you don't know how to communicate.
Yes. If you can't say it, you don't understand it, basically. In some way.
You don't understand it well enough.
Yes. You can understand something, but if you don't understand it well enough, you can't teach it, basically.
Yes. Or you can teach it by a program.
Yes, exactly. And I think even with regards to teaching, the reason why most people move away from teaching as a medium of knowledge and gravitate more towards reading and all that stuff is teaching is almost getting out of your comfort zone in some deep way. Like it's actually psychologically disturbing to go and engage with people and actually try to almost pass knowledge. At the same time, you feel insufficient. So if you feel insufficient about your knowledge and you're actually preaching it to other people, you have this almost like a cognitive dissonance in some sense, as opposed to reading and writing where you're just in your own cave and just doing whatever, I guess. So in that sense, from a self-critical perspective, teaching is very difficult. At least from my perspective, I never taught something, but even when I speak to people, I feel like I'm more hesitant than when I'm writing, for example, because I have this self-critical, let's say, psychology.
But it depends on why you're writing. Are you writing for yourself in a way that only you need to understand? Or you're writing, for example, writing in a diary, your thoughts in a diary, writing your thoughts in a book, or something for others to read, are two different complicated things.
Yes.
So it's two different processes.
Yeah.
You know what I mean? Teaching forces you to put it into the common ground. While doing something, you don't need to put it into common ground. You don't.
Yes.
I think that's essentially it.
Yeah, but I think even with regards to writing, if you're writing for audience, let's say people are going to read it, it's much easier than actually going out of your way and teaching to others. So that's what I'm saying. I'm saying like, even if you're writing for other people, you're teaching for other people, somehow teaching is much more difficult because it requires you to actually actively engage with other humans, I guess. So maybe I'm projecting my own point of view in some way.
No, I think teaching in a live classroom gives you more continuous loop. It's the feedback loop is more rapid.
Exactly, yes.
Writing, for example, has a shorter loop, a longer loop, feedback loop. Teaching, if you're conscious, you get the feedback loop is immediate, more in a sense. One, you read people's body language. Like I said, okay, you could tell me in a sense the end of semester evaluation or end of year evaluation will tell it's the feedback loop, but you're getting the feedback loop constantly. And that's why I believe teaching in person is better than teaching online. Teaching online, you cannot read the body language or the atmosphere of the room.
Yeah,
if that makes sense.
Yeah.
However, teaching in person, if the professor is engaged with the student, they get to know if they're doing a good job or not further.
Yes.
Right? If they're aware. So that's the difference.
Yeah, makes sense. So would you say that, like moving a little bit away from teaching, I guess, would you say that credentials are important with regards to academia, let's say? Would you say that a person who goes to uni and just progress with their academia, masters or whatever, is much more likely to understand the topic than a person who researches the topic through YouTube, let's say? Or that's not necessarily the case, because I think as we progress through time, the idea of understanding different ideas, I guess, is shaping itself more as a self-learning. So would you say one is more dominant than the other, or is it depends on the person? What would you say to that?
Can you rephrase the question, please? I don't understand the question.
So my question is, would you say that some form of rigorous academia is superior to self-learning or not? Not necessarily. Even with regards in the context of mathematics or any other thing.
Okay. We need to define what's a self-learning. Self-learning can be is learning something using your own sources and whatnot. Academia, your resources are set for you, more or less.
Exactly.
However, when it comes to BT, essentially in BT, you have to be a self-learner because you have to do something new. Why academia? Okay, each has pros and cons, right? Being a self-learner is an admirable quality. Academia just gives you, it's your gym to train at, essentially, to whatnot. Let's say you could work out on your own, you could work out with a coach, okay? If you have a bad coach, you're better off on your own. If you have an amazing coach, you're better off with them than on your own. Yes. Here's what you want to do. Now, how it's in learning, I believe you need feedback. Okay? For example, look at the athletes. Why don't athletes just train on their own? Because they need the feedback loop from an external eye.
Yes.
To remain objective. You cannot, because you're unconscious of what you're doing wrong. So, for example, in academia, you have someone who's coaching you in a sense. Either you're at different stages. For example, after a while, your coach becomes a journalist. When you submit papers to be published, you're going to get a loop. Explain this, do this, you need to do that. But you're going back to your question, which is better, I think it depends. You could have an amazing classroom, it's like each has its own, right? There are things you're better off on your own to learn. Essentially, if you need to think, if you need to develop your own way of thinking, you need to do it alone. So I think for theory, you can do both. For practicality, that's to learn how to code, for example, or do a math problem, you should do it on your own. Because you need to build yourself up. Self-learning is self-reliance, but academia it should be complementary. Now, let me tell you something. Is it needed? I think it's needed in a sense because you don't want unqualified people to be teaching. I could open my own YouTube channel and start blabbing, and that becomes a problem. I could publish false science on YouTube. There's a high probability of that, publishing false information on impressionable people. I'm not saying you should censor, I'm just saying the likelihood is higher.
Yes.
While in academia, still bad information can be published, but it's a low probability. So that's why it's different. Is it needed? Yes, it's needed because it's more controlled what is being published. Specifically in medicine, I'm not saying it can be too limiting, but it's essentially being conservative of what to say in academia.
Yes.
You have to be more conservative. When I say conservative, I don't mean in traditional values. I mean in conservative is you have to be careful of conservative in a way, and you cannot be too free in publishing. You have to, the ideas have to be very
reviewed, let's say.
Reviewed, peer-reviewed, but I think the more that I'm trying to say a different thing is the ideas that you publish have to have merit in them, if that makes sense. They have to have proven results in a sense, or some evidence, let me say.
Okay.
While you can do whatever you want to do and come up with your own thing and just spew nonsense around, right? So for example, that's why you have governing bodies for different things. Why do you have a governing body? So even for example, when it comes to martial arts, like they tell you who's your coach, right? Who's your coach, where is he registered, whatnot, because you could have somebody who's having a black belt, a fake black belt, or somebody who doesn't know what to do. So that's why lineage is important, right? I think academia is important for lineage. I mean, that's why it's like if you look at jiu-jitsu practitioners, they tell you he got the brown belt under this coach, black belt under that coach, that. Compared to, so lineage is important in jiu-jitsu. And in a sense, because it shows honor, not honor, I think a better way, not honor, I think it shows more merit, distinction.
Yes, proven results in some way.
No, it not proven results, but it shows quality.
Okay.
Quality. You know what I mean?
Yeah.
If it's like when somebody said I graduated from that school versus that school because it's more. There's evidence for quality.
Yes.
It's not proof. It's evidence of quality than. Anything else.
And I guess to put everything into context, you're just saying that the probability in academia is much more higher, but that doesn't mean that the person who's self-learning is not going to have quality. But what you're saying is the probability is higher, and if a person goes through both roads, let's say, rather than just self-learning.
Yeah, and also the opposite is like I'm not gonna say like you could have extremely stupid people who have PhDs or something. It's what I mean is it's not, again, it's not a sufficient condition or necessary condition.
Exactly.
To be. It's just a high probability. Somebody who goes to college have a hard, like it tells you, for example, they finished undergrad, it tells you a few things. One, they have commitment. Two, they have some sort of, assuming they did not cheat or whatever, they have some sort of a work ethic. That's why somebody who gets a 4.0, it shows their work ethic. It does not show their intelligence per se.
Yeah.
Because getting a 4.0 is damn hard, but it's not showing of intellect. You know what I mean? Going to a PhD and graduating from a PhD, it's different. I cannot vouch for that because I've not done a PhD, but I've seen very smart PhD people. But it's different. It's different. Like somebody who's graduated with a PhD, it shows that they've met the requirement, and that's why schools are different when it comes to PhD. Why, like, if you graduate from school A versus school B, it's different. PhD is a different ballgame than undergrad or even a master's. If that makes sense.
Yeah. So I want to move on to the last, I guess, point, which is with regards to the curious minds. So the place we met. So how would you basically describe your experience through it? So basically, for people who don't know, Curious Minds was a meetup group where Aziz actually made up a group where he had weekly discussions about different topics, intellectual topics, things like purpose and political correctness and all these other things. So how would you describe the 1 year of Curious Minds? Was it very much, let's say, an enriching experience, or was it as opposed to what you expected? How would you describe the experience?
So the intention of Curious Minds was, okay, I wanted to have people run it more than I would run it. I wanted people to suggest topics and take lead. And I wanted to give a chance for everybody to lead. However, I realized that's not possible because I believe at a certain point I got some topics from certain people, from some people, that it meant to be as it's meant to be as a neutral ground. One, I realized honestly, it's difficult to have a completely open. I never believed in. It's a difficult thing to wrap my head around. The intention of Opening Curious Minds is to have open discussions for people. Like people choose topics and whatnot. One, people did not choose topics much. I ended up choosing most of the time. And what I realized is the discussion would go better when I knew more about the topic. Then, I had to be more knowledgeable. That I cannot use a topic. When I used topics that I did not know much about, the discussion was kind of
dry, I guess.
Not dry, but chaotic.
Chaotic.
Yeah. When I picked a discussion that a topic I knew about, it was interesting. Either I would hear something new about that topic, or I would force myself when I'm discussing to ask different questions to challenge. But when I did not know, it didn't work. But the other thing I learned is not all topics should be it's difficult to have an open discussion in public with people you don't know. You don't know what they know about the topic and expect enrichment. It's pointless. So essentially, if I go back to academia, if I want to, if you go in an upper level class with prerequisites, you'll have a healthier discussion than if you go to that class without the prerequisites, with people without these prerequisites. So, in a sense, I think the discussion taught me why in academia there are prerequisites, because you need to understand. There's a reason why the prerequisites are chosen. Sometimes the prerequisites are chosen in a strict way in some sense. But for example, you should not be in Calculus 3 unless you finish Calculus 2 or Calculus 1. That's definitely a must.
Yeah.
But for example, I don't need to have taken any calculus class to do linear algebra, for example. I think that's what made me understand. The other thing is, in terms of a discussion, my experience was in I think by the end, before Curious Mind, I was also in different groups for 6-7 months. It's different. Having it's complicated. Because having discussions open to public opens the door for agendas. It opens. People don't come with the same intention. I would say that. It's different. Not all. Some people come in because out of emptiness. Some people come in because genuinely they're more or less they're looking for companionship. Now, when I say companionship, is not a friendship. I mean they're looking to meet someone, and that was not the intent. So it's very difficult. I don't know if that applies to other places, but that's what I've seen. Even in other meetups. I think because there was a limitation for us in a while, there weren't so many open, we were closed off inside for a while. So it's now when things are opening, people are eager to try things. And maybe because considering I studied outside and whatnot, when I experienced something, it's I've become more selective because I was exposed. Being exposed is not a good thing or a bad thing per se. It's what you make of it. But being exposed to things teaches you who you are. It teaches you who you are. So
if I'm gonna go back, for example, when I was to school, I was thinking, let's say, because it was mandatory for me to take gender classes, equality classes. Going to that side, it teaches you that, like, why or why not your values are right. Go to the opposite direction to teach you why you were right or why you were wrong.
You have to be open, I guess, minded enough to understand where you're wrong and where you're right.
Yeah, so that's why the point of discussion in the group is like I wanted somebody to come and challenge me, to challenge my beliefs. But I think what I'm thinking about now, next time you have to like always take the opposite stance to either weaken your stance or strengthen it. Don't take your stance. I think that's one of the things I learned from discussions is go to the opposite direction.
Yeah.
Then once you go to the opposite direction, understand it. With the intention you want to reach the truth, not with the intention you want to prove yourself right.
Yes.
You know what
exactly. Yes.
But in discussions, again, go back to discussion, people, I think you're going to meet all kinds of people. You're going to meet people who like the sound of their own voice. You're going to meet people who genuinely want to come. But it's running a discussion group, I think you need people. I think it's better to accept people cautiously a bit, because then you could not that when I say cautiously is so you have a better discussion. It's I think everybody is able to learn, but everybody's capable of learning and growing. But it's not the responsibility of the others to help them grow or force them to grow. I'll give you the chance to come and grow, but if you don't grow, I cannot help you. You know what I mean? It's like I sent you that. That's it.
And was the expectation different than what happened? So did you kind of expect this, or was it a completely different expectation? Because I think we usually set some kind of expectations, and then it turns out to be different. Like with cars.
Yeah, because I don't think I've ever expected anything. I gave up on expectation because I had at least 2, 4, 5. It depends. I think I always had at least one new person each meetup. So each person would throw a time on one meetup. I had 40 people, and I had to split into 3 groups. So it's different. It's complicated. But the interesting part is of running the group. People always keep discussions related to romance, purpose, and meaning.
Wow.
These are the 3 highest discussions that people came to. If you choose more of a niche topic, people will shy away.
I think that's why also Jordan Peterson is too popular, because he usually speaks about the 3 things you mentioned in some deep way. Like he usually speaks about meaning and I guess purpose, romance, like marriage and all these other things.
Yeah.
So I guess that's why he's too popular. So that's interesting to think about, even from my perspective.
Because people can understand what he's talking about.
Yeah.
He's talking about a related problem, if that makes sense.
Yeah, relevant. Yeah, that makes sense. So anything you want to say before we go off camera?
No, not at all. Thank you so much for having me. I enjoyed this way more than I always knew I would enjoy talking in a podcast just for fun, but I think this is way more enjoyable. And yeah, it was fun, and I'm very honored to be your first live guest.